It's so pleasing in the eyes, isn't it? Have you ever wondered how the waters carry the lights in this colorful and adoring fountain display? So, let us know what is the science explanation behind this eye-catching fountain display. Good day everyone, I'm Danilo Tatat-Lordilis, a third-year student of Central Bicol State University of Agriculture, Pili Campus, and I am your future science educator. A while ago, you have seen a colorful and adoring fountain display. Honestly speaking, there are engineering applications in that display, but in this video, we are more concerned with the science or the physics explanation, which is the total internal reflection. So, at the end of this video, you will be able to, first is to explain what is total internal reflection. Second is identify how total internal reflection occurs. And lastly, you will be able to solve problems related to total internal reflection, particularly in finding the critical angle. So now, what is total internal reflection and how does it occur? Total internal reflection. In physics, it is a complete reflection of a ray of light within a medium such as water or glass from the surrounding surfaces back into the medium. There are two conditions must be met in order for the total internal reflection to occur. First is, the source of light must be in the more dense medium and approaching the less dense medium. Second is, the angle of incidence must pass through the critical angle. Okay, since we already know what is total internal reflection and how does it occur, so now we are going to ray diagram the total internal reflection for us to visualize and better understand its concept. So now let us use ray diagramming to better understand the concept of total internal reflection. So let us consider this line is the interface between medium 1 and medium 2, wherein medium 1 is less denser than medium 2. And let's have a normal line here. And let's say that a ray of light is traveling from medium 2. This angle is what we call the angle of incidence. And when the ray of light travels from medium 1 to medium 2, it will refract into an angle. And this angle is what we call the angle of refraction. And angle of refraction is greater than angle of incidence because we all know that medium 1 is less denser than medium 2. So if we increase the angle of incidence, it will refract to an angle wherein the light will never escape from medium 2 to medium 1. And this angle is 90 degrees. And this is what we call the critical angle. So considering the second condition in order for a light to undergo total internal reflection, which says that the angle of incidence must pass through the critical angle, we can say then that if we increase or the ray of light travels greater from the critical angle, total internal reflection may occur. And by that, we can say that in finding or knowing if the light will undergo total internal reflection, we must know first the critical angle and place the source of light greater from the critical angle. So now, I'm going to teach you on how to find the critical angle. So let's consider this problem. So in solving this problem, we will use the Snells Law formula, which is index of incidence, or denoted by the big letter N and small letter I, times sine theta critical, or the theta, is equals to the index of refraction, denoted by a big letter N and small letter R, times sine 90 degrees. So in solving problems, we must write first the given, and in the problem, the given are the index of incidence is 1.5, and the index of refraction is 1.33, and the theta critical or the critical angle is unknown. So since we are going to find the theta or the critical angle, so we will derive first this formula. index of incidence times sine theta is equals to index of refraction times sine 90 degrees. So first, we are going to divide both sides by the index of incidence. And then we are going to cancel out this one. So the formula, it will now be sine theta is equals to index of refraction times sine 90 degrees over index of incidence. So to omit this sign in this side, we are going to inverse it, and the formula will now be theta is equals to sine raised to negative 1 times index of refraction times sine 90 degrees over index of incidence. So this will now be the formula to find the critical angle. So in finding the critical angle, we will now substitute the value of the index of refraction and the index of incidence. So it will now be theta is equals to sine raised to negative 1 times the value of an index of refraction is 1.33 times 1, because 1 is the value of sine times 90 degrees. And even when you click it on your calculator, sine 90 is equals to 1. So the value of sine 90 degrees is equals to 1 over the value of index of incidence is 1.5. So 1.33 times 1 is equals to 1.33, and 1.33 divided by 1.5 is equals to 0.8867. So it will now be theta is equals to sine raised to negative 1 times 0.8867. So when you click it on your calculator, just shift sign times 0.8867. So the answer is theta is equals to 62.46 degrees. So in this problem, the critical angle is 62.46 degrees. Hence, for the ray of light that travels from glass to water to undergo total internal reflection, it must be placed, or the source of light must be placed on greater than 62.46 degrees. So it is like the fountain that you have watched earlier. The source of light was placed greater than the critical angle, and that's how it creates a total internal reflection. So I hope that the topic total internal reflection is you understand it well. And once again, I'm Danilo T. Flordelis, your future science educator.
Physics is a branch of science that deals with motion, light,